Muthu is an associate professor at Georgetown and co-founder of Ligero, and he'll be talking about how we can use Ligero or Ligatron to compose zero-knowledge proofs in the browser. So thank you. Welcome, Muthu.
Thanks, Cathie. Hi, I'm Muthu. I'm co-founder of Ligero and associate professor at Georgetown University. I'm going to talk a little bit about ZK today and what we are trying to do at Ligero. So this is where it all began, in the work of Goldwasser, Micali, and Rakoff, where they introduced the notion of interactive proofs and zero-knowledge interactive proofs. These are proofs that convey no additional knowledge beyond the validity of the statement. I will say that if you haven't seen either Shafi or Silvio explain zero knowledge, I'd encourage you, I'd excuse you even to leave my talk and go find some YouTube video to watch them talk about zero knowledge. And I'll challenge you that it is impossible to not fall in love with zero knowledge. Today, with the advent of blockchains, I want to say there are so many companies, so much research that is going into zero knowledge. This is just sort of a slice of what's happening in the blockchain space. And there have been billions of dollars invested in developing these proof systems. And our company is also one of these that have been received investment in this space. So let me talk a little bit about taxonomy of proof systems and how how I look at this landscape. So when it comes to proof systems, there's the traditional interactive version, which is more designated verifier, and the ones that are snarks, non-interactive. Some of them, or most of them that are used, are publicly verifiable, meaning that you can generate the proof once and any number of people can verify it. There are the kinds that require a trusted setup, like a common reference string, and the ones that are like hash-based that are called transparent, that don't need trusted setup. There are proof systems that offer only soundness or integrity, but offer some efficiency, while there are others that also give the zero-knowledge privacy property. And again, you can classify them as succinct or not succinct, depending on, again, proof length, verification time. And another classification is what kind of crypto they need. Do they need public key cryptography or symmetric key? Again, this choice can influence whether you want post-quantum or not, as well as there are also efficiency reasons to go from one to another. I want to say that the ones that I've marked green here are, in some sense, more desirable. And in a spectrum of these kind of proof systems, I want to say that what has emerged is ZK snarks, starks, or snarks. They provide a very useful property of being non-interactive succinct verification, and indeed has found a lot of applications. What can you do with zero-knowledge proofs? I know I'm kind of preaching to the choir. You all know what you can do with zero knowledge. When it was first discovered, one of the first applications was about amplifying security from semi-honest to malicious. It was about proving honest execution of protocols. Soon they found identification, eCache, and what can you prove? Well, everything provable is provable in zero knowledge. But today, all of these applications are really coming to reality. A lot of the proof systems, the ZK landscape actually are focusing on scaling blockchain, which I'll tell a little bit more. And the talk you saw before and the next 3 talks, you're going to hear a lot about anonymous credentials. And of course, in the blockchain space, you want confidential transaction, anonymous transactions. Again, a lot of work in using zero-knowledge proofs to enable this is coming up. Zcash, Alio, Aztec, some of these companies that are trying to do this. And of course, there are many new interesting applications that are coming. Image transformation, expiring proofs. This is a very interesting example. Come and ask me later. I don't want to spend time right now. Fog of war gaming. This is also another thing that you can enable, like peer-to-peer gaming using zero-knowledge proofs. Now, I want to classify these applications in a slightly different way. I want to say that there are applications that you want to prove something about sensitive information. These are the ones that are privacy related, run client side. And there are ones that are proof systems, which focus on verifiable computation and can run server side. And again, just listing some of these applications that fall in either of these categories. And I want to say, again, anonymous credentials being one of the big applications client side, and blockchain scalability being the ones on server side. And clearly, for the ones that require privacy, you want the zero knowledge feature. And for the delegation, you want, succinct verification and snarks are sufficient. So where do modern zero knowledge fall short in the ones that require privacy? I want to kind of focus more on the ones that require privacy in this space. So most companies that actually build, they're doing blockchain scalability. They don't need zero knowledge. They are focusing on snarks and starks. They are not zero knowledge. The ones that are ZK snarks, the ones like Groth16, et cetera, they require a huge memory because they need a huge proving key for the trusted setup. And the ones that also deliver ZK, they're not yet scaling enough on the client side. I can't do very large computations fast from the client side. And finally, the ones that also do these things, they require developers to learn sort of a new language, like a new DSL to program in these things. So Vitalik, one of the thought leaders in the blockchain space, of course, just recently or last year mentioned that privacy use cases haven't come to client-side proving yet because client-side proving haven't scaled enough. So what are the challenges in building and deploying these zero-knowledge applications? First, data needs to be attested. Second, you need standard toolchain for developers, not new languages. And finally, I kind of want to say one of the technical bottlenecks is that zero-knowledge proofs, at least the way they are designed, are inherently memory inefficient. So I want to talk just maybe 1 minute about this data, like each of these points. Data attestation is about, hey, I need data to be attested. Otherwise, what kind of sensitive information am I proving if I don't have authentication on the data? And there have been like really novel mechanisms to get attestation, even though we don't have trusted institutions that are willing to digitally sign your data. Here are a list of them. ZK email that allows that you can actually prove receipt of any email or even properties of your email. ZK login, again, another mechanism that actually is trying to revolutionize how you have digital wallets by changing your wallet address to your email address. And zkTLS, finally, I think this is a really interesting new idea that can help get all of like sort of Web 2 information or the ones that you do in TLS communication authenticated. I'm going to talk about zkTLS a little more. I want to point out that all of these have been deployed in production in some form. So what is zkTLS? It's about trying to enable attesting a TLS payload. How does TLS work? Well, there is a browser and a server. You have a handshake where some information is signed by the web server, including its identity. And then there is a session key that is generated with which there is encrypted information. Now, as it is, of course, even by design, the browser cannot prove information about the information received in this TLS payload. And the answer is simple, because both the parties have the session key. You can forge any message post-communication. I cannot prove that a communication occurred with authenticity. So here are two mechanisms in which you can do it. One is using a proxy. You have a person in the middle that is willing to sign all the information. Now a browser can prove that, hey, look, I did do this communication. I have a signature of the handshake, and that I have signatures on all the encrypted communication, and then I can show that the decrypted payload is something. For example, your back statement has greater than X dollars. But this is not that desirable. There is an easy attack. If this proxy is not looking at anything, I could get fake encrypted messages. I could get incorrect encrypted messages signed. A second approach is something called a trusted notary, where you can imagine that the trusted notary and the browser act actually as a two-party computation to emulate a single party in this TLS communication. In this way, the session key is not stored at just the browser. It's secret shared between the notary and the browser, and every time you have to do encryption or decryption, it becomes a two-party computation protocol. And now the browser can generate a ZK proof of, again, first that the handshake was signed by the bank, and then all the transcript. In addition to being a 2PC, the notary also signs, the payload, and you can prove that this decrypted payload, in fact, has whatever you want to talk about, the data you received from the server. So this is how zk-TLS enables doing this, getting this data on to get attested. So I'm running a little slow on time, so I'm going to tell you the second thing I've talked to you about, like representing these things. Today, actually, there are ZK systems that can prove standard VMs like RISC-V and WebAssembly, and these enable now you to develop applications in a high-level language. The last thing I want to tell is about the bottleneck in designing ZK systems running client-side. This is memory efficiency. And on a high level, again, the two things is that ZK snarks that require trusted setup, again, huge prover key that you need on the client's device, and the hash-based systems, which are really in practice much faster than the others, have a space-time trade-offs because they require error-correcting codes. And there are some lower bounds in why this is indeed the case. So what I want to do in the last couple of minutes is to talk about this platform that we have designed. This platform will enable you to develop and deploy zero-knowledge applications straight from the browser. You can enter a C program in the browser, compile, deploy, and make it available for anyone. So here is a short video, and I'll try to talk through this video while we're doing it. This is open for everyone. You can log in with your Google credentials. Once you log in, you'll get into this marketplace where we have tested a few applications over here. I'll show one of them in this video. But first, I want to point there is a speed test which you can run. It will tell you how fast your device can prove zero-knowledge applications using the Ligero proof system. Here, I have run it. It reveals some number. Roughly, if you want to get a measure of this number, it says that you can do about 20,000 Poseidon hash functions per second. And the number really is about how many constraints per second you can prove from your browser, if you know what that means. So now I'm going to walk through designing an application. You can create a new application in C or Rust. And what you have to do is you have to write a C code straight in the browser. There's a little bit of plumbing in terms of assertions you have to do. Here, I've coded an edit distance applications that measures the edit distance between two strings and shows that a private string is close to a public string. So you hit compile, and when you hit compile, it actually goes to a backend server. This is the only thing that goes to the backend server, compiles to WebAssembly using a standard LLVM compiler like Mscripton, and the WebAssembly program is brought back to the browser. Then you provide inputs to your program. Here I'm giving the two strings that go as input to this program, and I'm showing that the first string is close to the second string. I need to, and the second two strings, just the second two inputs is about the length of these things. And once I give these inputs, I have to mark which one is private, and I can prove. And this runs completely from within the browser. And if I have a little bit of time, I'm going to talk about benchmarks about this system. You can deploy this thing, and it will go to the marketplace. And I can tell you a little more. I'm going to actually skip to the benchmarks. So right now, I want to say that one of the first ones that got designed in this space is Circom, which designed a front end to prove using Groth16. This has a limitation in terms of its prover key. If you want to run this on an iOS device, you won't be able to run beyond 1 million constraints. And you actually saw that in my demo, I ran more than 4 million constraints. NOAR is, again, another system that's getting around these lower bounds using this new concept of incrementally verifiable computation. Our system currently, again, there are different trade-offs between these two things that we are we are 10 to 20x faster, but there are different trade-offs between our system and the NOAR system designed by Aztec. So finally, I want to say what we are trying to do is that we want to make developing these ZK applications easy. We want to, all you have to do, you can run everything from the browser. You can do it in any languages. We are trying to provide support for more and more languages, and we want to be able to deploy it on any device. We want to make this toolchain easier. We hopefully, we will include all the cryptographic primitives you want: ECDSA, EDDSA, SHA. Our system is post-quantum, so we hope that this can power sort of the next generation of ZK applications. Thank you.